Okay, hello everybody. Try to make this exciting in this big room. So I'm deal with the echo a little bit. So I'm Byron Ruth. I am the VP of Product and Engineering at Synadia. I've been a NATS user and long before joining Synadia. Very happy with learning the technology, and the creator of NATS is actually sitting right over there, Derek Collison, and so you can say hello after the talk. I'm a NATS project maintainer under the CNCF, and fun fact, I was in pediatric research for 14 years prior to actually joining Synadia, and I used NATS actually while I was there. So quick show of hands, who knows NATS? First of all, just put your hand up if you've heard of NATS at all. Okay, keep your hands up. Who is dabbling with it and building little applications with it? Trying it out on the side? Okay, who's using it in production? Oh, so some people actually put their hands back up. That's interesting. Okay. And who hasn't tried it at all? You just heard of it. Nice. All right, perfect. That's a very nice mix. All right, so I'm going to go through a few, quick intro slides. This is a maintainer track talk, so I want to make sure that everyone's sort of like caught up generally. And then we're going to sort of do like a state of NATS, what has been going on in, this past year. So generally as a project, as we know, it's a incubating CNCF project. We are trying to move forward with the graduation process. From a purely, there's a whole ecosystem around this. So there's a NATS server, which is sort of the core project that has been contributed. There's a bunch of client libraries. There's the 11 official ones. There's a whole bunch of community ones that have been contributed, which is great and available on GitHub that are open source. Our community is massive on Slack. We have Google Groups, we have Slack, we have different channels for communication, which has been fantastic. At any given week, there's probably 400 to 500 active people on Slack to answer questions and help you out and get you started if you're completely new or if you're advanced and you're like, I have no idea what's going on. All of the Synadia maintainers are also in the Slack actively every day, so you can ask us questions. And there's a lot of downloads, there's a lot of open source usage around that, and from a Synadia side, we have a lot of really great customers as well that use it in production. So going back to what is NATS, like what is the overarching idea behind it? There's a bunch of roles involved when you're building systems, and NATS sort of originated from this idea of starting simple. I need to solve this sort of like core plumbing messaging problem, and then it sort of grew out from that foundation, and we'll get into that foundation in a second. But as NATS has been developed, all of the different roles of sort of who's involved in actually developing, architecting, operating a system has been kept in mind in various ways. And so I'm not going to read these lines, but developers, and we'll see, it started in a very simple, request reply pub sub type of messaging. Jetstream, for those who are aware of that, that's our persistent subsystem, and this is more equivalent to something like everyone knows of Kafka, right, or Red Panda, those types of things, and it's basically a durable persistent stream, but off the abstractions of what our core NATS provides. And so you get streaming. We built KV and object store abstractions on top of that, and then you have, basically these client SDKs that you can just use. And so the idea is that from a developer standpoint, you sort of have all of the tools, right there, and you don't have to reach for another dependency externally. You don't have to say, oh, I need my Redis, I need my, external object store. And there's like, trade-offs. We're not in parity with, either of those specifically. But if you need those types of primitives when building and considering your application, you can just use this one core technology. And there's a lot of advantages of that, which flow into sort of the architects and operator roles. Because as a developer, you're like, I need to solve my problem. I need to, store some data somewhere. I need to be able to like do request reply over here. I need to broadcast a message over here. But then you're like, oh, how do I actually, distribute this thing? You could start on your laptop, and this is sort of the beauty of NATS, of how it's designed. And I'll show this later in the talk. You can have your whole NAT system literally running on your laptop. It could be a single server, or you could have a giant supercluster, let's call it, all modeled on a single system. But if you actually distribute that and actually place it on physically distributed nodes, it's all the same to the developer. It's all the same to that application. So an architect, their mind is going, well, we're trying to serve our customers. We're trying to, decrease the latency to services and data. Where should I actually physically place my NAT servers? And then correspondingly, the client applications that are connecting to those. From an operator's perspective, they're like, I want multi-tenancy. How do we apply, auth N, auth Z? How do we apply different security constructs? All of this stuff is baked directly into NATS, out of the box. And that's, very much intentionally by design. So what is NATS, but why NATS? Like, why should you care? This is my quote that I just came up for this talk because I'm up here and I can say this. But I was reflecting on this and I was like, when people say why NATS, and I mentioned I started using NATS long before joining even Synadia. I was a very happy open source user. And over time, when you start using this, and I said you start very simple. It sort of has batteries included. You start sort of building up, I'm a developer, I'm solving my little problem, and then I have to figure out how to distribute my either topology of the NAT servers or my application, and then I have to think about like multi-tenancy and authorization, those types of things. And over time, and I'm trying not to be biased, but I have not come across a technology that includes all of that stuff that I don't have to, bring together all these external dependencies to solve the same problem. And it does it in a very, very nice and fluid way that I don't have to, because if you think of like multiple dependencies that you're trying to bring together, how do you bridge the gap between the security layer, as an example? Like you have to come up with something around that. You have to think about, if you're operating it, especially if they're not managed services, you have to figure out, you have to have specialized teams to know how to run a Kafka cluster or a Redis cluster or something like this. And this is just NATS, and you just operate NATS and you get to use all of the things that are already built into it. So this is one of those things that like over time you get used to it and you're like, this is lovely. And then it's difficult to kind of go back. But going to the foundation, like why NATS? It's because it's really based on a completely different foundation from how other technologies for distributed systems are actually designed. We think about like microservices. People think about that. There's different people are like, monolith, microservices. I hate microservices. You probably didn't design a microservices system with NATS. That's probably why you don't like it. So I'll just throw that out there. So one of the foundational, challenges that exists when building distributed systems is that you have to deal with a whole, like these, 3 core things. You have to depend on sort of the location and networking land that's like, I have an IP address, I have DNS that has to resolve somewhere, I have to have a service discovery, service somewhere to resolve, and things are moving around. And some of that is abstracted with you within Kubernetes or like, service mesh technology. But there's layers upon layers, And again, NAT just solves that out of the box by itself. So it's one unit. The other big one is sort of the one-to-one communication. So we're custom, everybody knows HTTP. It's fantastic, it drives the web. It is great for the web. It is not great for distributed systems. This includes gRPC, and that might be a hot take, but it's based on HTTP too. It's still point-to-point communication. You get streaming, it abstracts that away. You can do, point-to-point streams. Great, that's fine. You still have to know which service you're talking to at any given time through discovery, some kind of mechanism. And then similarly, sort of following along that, which is a little bit more nuanced, which is sort of the synchronous interactions. The thing that is there has to be there before I can, talk to it, right? And it has to be available. And so what ends up happening is that you get into this flood of like circuit breaking and retries and all this kind of stuff. The more and more you kind of chain calls together, which can be very challenging to kind of diagnose. So NATS took a different approach of saying, let's just change the foundation of this. Let's think about it, not radically different, but just from a different perspective. So the core of NATS is sort of, it relies on subject-based addressing. And so what all that means is that once a client connects into NATS, it is brokering all of the communication to all other clients that are connected. No matter the topology, no matter where those clients are connected from, it doesn't matter. You don't have to know where that other client IP address, the DNS of that client. There's no point-to-point, direct point-to-point communication there. And you get a lot of affordances from that. End-to-end communication, similar thing. Let's not assume point-to-point. Let's allow for, you can still achieve, end-to-end means you can also do one-to-one. You can still achieve request reply, but this provides a much more, flexible way of achieving it. And then the asynchronous interactions come in twofold. Sometimes you do have to physically, you do have to wait for something, and like, if I don't get a response, then I have to move on. That's a choice of an interaction, but you should not be forced into that interaction pattern. You should have the ability to publish something, and you might be able to, spatially decouple, which is the whole location independence aspect. I'm physically somewhere else. There might be a responder over here that can take my request. There might be someone over here. I don't care. I just want to send the message. It'll get routed where it needs to get routed, and then it gets a response, and I can, go about my day. And then the temporal decoupling, which we'll get to, is around Jetstream. It's a streaming aspect. And the temporal decoupling simply means I can publish a message. It's going to go maybe in a stream. It's going to go in a work queue. It's going to go, one of those. The consumer on the other side will pick it up when it's ready to. Publisher doesn't care. I sent the data. It's there. You pick it up when you want to. All this is baked in. So sort of like the overarching idea behind this, and sort of like, the pitch, let's call it, and, in very glossy, words, we're trying to achieve this, secure and coherent application technology. And for services and data, so this is your communication patterns, your interactions. We have the persistence layer, that's your data. These are your KV object store abstractions. But interestingly, and we'll see this a little bit more in the second section, which is sort of like, beyond clouds, geographies, edges, meaning that you can create and construct your topology. And Derek always says this, which is like, you can Lego brick NAT servers together to kind of create whatever topology you need to achieve your system requirements. And that's genuinely true. And it's very cool. So, transitioning to our second half, and I'm doing good on time. Now this is going to be more fun and interactive, I hope. So, state of NATS, the main thing for those who have been existing NATS users and you've been tracking sort of releases over time, we made a significant shift in sort of how we time our releases. And this is just simply to illustrate that 2.10 was released back in September 2023, and there was an 18-month gap between 2.10 and 2.11, and a lot of stuff went in it, and a lot of work went into it, and it's there's no shame, let's call it that, but we're like, we want it to be a little bit more regular. We want it to be a little bit more predictable. We want to sort of like constrain the time, down, and then we have fixed time variable scope. It's more predictable for everyone that's sort of involved. And so 2.11 was released in March of this year, and then 2.12 was our latest release just back in September, and then we have plans for, and the cross out of 2.13 is, you can ask Derek afterwards. 2.14, we always skip that version, 2.13, 6 months after September, so March 2026. So given we've had 2 releases this year, we've had a lot going on. So this is sort of a little mini deep dive, as quick as I can go, sort of on the left-hand side. We're going to go through some examples today, and then what we're not covering, and there's a plethora. You can go on the docs.nats.io. There's sort of a what's new section, and you can sort of see the release notes for 2.11 and 2.12 and an upgrade guide and all that kind of stuff. But these are sort of like some of the highlight features that have landed in 2.11 and 2.12. So they're available for use. So I'm going to basically go through a few demos on the left-hand side today. Just if you've heard of them, if you haven't heard of them, if you've heard of them but you have no idea what they mean, I'm going to try to debunk a little bit of that. So I mentioned before that you can get started with NATS with a single server running on your your laptop. Well, I have this system running on my laptop. So just to showcase this, there's the little blue circles are 3 individual NATS clusters. The blue lines represent that they are called gatewayed together, forming a supercluster. And if that doesn't mean anything to you, that's fine. We'll touch on that. And then the purple little dots on the side are leaf nodes, and those are still NAT servers, but they're connected as sort of like these independent entities that are sort of plugged in, and they have sort of their own authentication boundary. And I won't get into the minutia of that right now, but we'll kind of unpack that as we go through. So not all the examples are going to leverage all aspects of this, but some of them will. So I just wanted to kind of show that up front. So the first, main thing. So we're always thinking about, the talk is like performance, scale, flexibility. We're always trying to push the boundary. We have, our experience of our own customers, pushing the boundary all the time. You can go on, the website, but we have, plenty big name customers that have very, very large deployments, very large topologies, a lot of, things running, let's call it that way. And they're always wanting more. They're always like, who doesn't, right? So they're always, an activator for needing to increase performance or scale or something like this. So that was sort of the motivation of the talk, to sort of talk through the features that have been implemented that have been driven by a lot of that kind of demand. And there's always trade-offs. This is one such, and we have plans in 2.14 to further expand the spectrum. But the basic gist of it is that, and I'm not going to get in. There's a better chart that my colleague threw together last minute to help me explain this, but the gist of it is like we're decoupling, for file-based storage, we're basically decoupling sort of like the flushing to the OS kernel from the application, which is NATS, and then from the kernel. And for anybody who has like read Salvatore's Redis blog post, is like classic one of flushing and syncing. If you haven't, you can go look it up. It was written like 15 years ago or something. It's a good one. But the point is that there's 2 sort of layers to persistence or durability, let's call it. And so you have to tune it depending on sort of like the trade-off. And so in this particular case, this is sort of the trade-off that is observed, and sort of what was implemented is being able to push the boundary on ingest rates and performance. And this is sort of on the right-hand side. You can go faster, and this the top line is sort of a R1, which simply means it's not replicated across multiple nodes. It's a single stream on a single node, and you're just relying on that. It's going to be, that node is not going to go down, So you have basically a spectrum, but you have the knobs to be able to tune this as you need it, and there's different use cases that require that. On the bottom section, this is 3 or more replicas, which we generally always recommend unless you can tolerate loss of data. R3 replicas, some people use R5, depending on, again, the use case. But that is much more safe. It uses the RAF consensus protocol to be able to replicate across, a quorum of nodes. And then so at the very least, before you get an ACK back to the client, you ensure that there's multiple replicas that have been on separate hosts. So You can ignore a lot of that unless you want to go deep and you can talk afterwards. But the gist of it, assuming it's visible, so this is showing basically different message sizes on the left-hand side, the flush type, which is like batch 1, batch 100, and then batch 500. Shouldn't be flush type, it should be batch size. But basically, you're writing one message at a time. You're writing 100, you're writing 500. And basically, from a synchronous versus an asynchronous flush perspective, if you enable it, you can see on the far right side the throughput difference. And there's a couple anomalies which could have been just my local hardware, freaking out at the time. But you can see you kind of get like 10 to 30 to even 100% increase of throughput based on this mechanism. So if you simply enable this as a stream option, you can get a whole bunch more throughput. And at the bottom, you can see like 175 megs. And again, this is on my machine, my hardware. It's going to vary, of course, but it's like a little micro bench for a direct comparison. For an R3, we have similar thing, but it's an R3. It's replicated, but you can also see sort of the throughput difference between 211 and 212. We use some of the async flush behind the scenes. It's not a direct flag that you enable, but you still can achieve, a much higher throughput. And so this is just basically a free performance gain going from 211 to 212, which is kind of nice. With no reduction in safety, because it's the exact same parameters. You still get the RAF log, you still get the RAF replication. We're not giving up on safety. It's just we're taking this optimization and sort of like adding it in the layer of the stream flush. All right, I need to pick it up a little bit. So we have atomic batch publish. This is really focused on basically sending messages atomically, and you get all of them committed or you don't. It's that simple to a stream. So I'm going to quick jump over here. Glad you can see this. Is that legible or not really? I'll try to bump it up a little. Is that better? Yes? Yes? All right. So I'm just going to quick reset my streams. I have my little guide over here. So all I'm doing is I'm creating a stream. I have this new flag, and this is all through the CLI. The CLI implements. You can do this through all the various client libraries as well, but it's simplest for demo purposes to show this. It's nice and quick. So I'm creating an event stream, and this is going to be the same type of stream all throughout with maybe different options. And I have this option called allow batch. Great, created it. It's not exciting. I'm going to subscribe to the stream on the bottom here. So this is just saying, it's creating an ephemeral consumer. It's just saying, yeah, great, I'm subscribing to this stream. And just to demonstrate the standard behavior, which is when you publish a message to the stream that's been accepted, and you can see stream event seek 1, then of course the subscriber, the consumer behind the scenes, is delivering that message to the terminal. Now, if I do that subscriber is still alive, and I do a NATS pub, and this is just the weird incantation for atomic, it's going to throw me into say, great, every line. So hello, KubeCon 2025. So if you look at here for a second, adding 5 bytes, it published to that subject, it published another message, so we have 3 messages. Notice nothing came through on the subscription side. So those are staged as a batch. And then I end it, and then it comes through on the subscription side. And you get this additional metadata, which is the batch ID and then the relative sequence ID for that batch. And it all gets flushed out, and it gets actually delivered once that batch gets committed. Pretty cool. So that's a quick one. Consumer pausing. This is a subtle one, but pretty useful. The basic gist of this is show by numbers or color by numbers. So we'll reset this guy, create our stream again. That's cool. And then we're going to publish 100 messages. So that stream is pre-populated with 100 messages. I'm going to create a consumer. And you notice this additional flag that says pause for 20 seconds. Actually, because in the interest of time, I'll pause it for 5. So what's going to happen? Oh, well, I need a sub, so I'm probably not going to be fast enough. Oh, no. Oh, it already went. That's all right. So what this does, I'll show it in the next one. What this does is basically create the consumer, but don't deliver anything until after this pause time. And you can set like a duration, or you can set an absolute time. So that's one use case. The other one is if I do NATS at runtime for that consumer, I can actually just pause it and say, just pause for 10 seconds. So that's sending a message to the consumer to say, just pause, and says, you really want to pause? Yes. And then what I'm going to do is I'm going to publish another 100 messages. Nothing's going. And then it just went. So you're able to delay. And the use case behind this, and you can also pause indefinitely, and you can resume as well. You don't have to specify a time. The use case for this is sort of like operational needs. Let's say your system is getting overloaded. Let's say you need to just say, just stop delivering for a second, for a few minutes. I need to move stuff around. I need to, stop delivering to my applications. Maybe there's a weird, poison pill or something that's going south. Just stop delivering. Let me, pause it, redeploy my application, and then you can, proactively resume it. This one is quite cool. So this is expected subject sequence. So this one is, I realize I'm running out of time. This one was really purely driven by event sourcing use cases. So does anybody apply any kind of event sourcing, or have heard of it, or interested in it, or anything like that? Yes. So I won't belabor this too much, but it's just generally useful. So the basic idea is that we have this optimistic concurrency control within NATS. So you can basically say, I publish a message to a stream, it gives you back a sequence number. And I can provide that sequence number as a header to say, only accept this next publish if the sequence number matches. It's very simple. So you can basically ensure at a stream level or a per subject level that you can guarantee the versioning is lockstep. The sequence number is lockstep, that you're not going to deal with this like dual write problem, and you have competing writers. That's the whole idea with OCC. What this does, and I just, again, in the interest of time, what this does is basically allow you to say, I want to publish on, let's say, events ordered 1 created, and I want to provide a sequence number, but I want to match it against this events ordered.1 greater than, or some wildcard. So all that means is that when it actually does the assertion against the sequence that you've given it, it's going to match against that pattern rather than the concrete subject that you're publishing on. And so for those who are aware of event sourcing or domain-driven design with an aggregate, if you've heard of that term before, the idea is that like everything must flow through that aggregate. That is the transactional boundary. And so you can actually model that exact thing within in NATS now, using this additional header, which is really great. So mirror promotion. This one is fun. Just gonna get through these, and we'll have some time. Even if we run out of questions, we'll be here all day. So this one, the idea is that who has used stream mirrors before? Have you know what a stream mirror is? Have you heard of a stream mirror? So the idea of a stream mirror is that you can create a stream, You can create a mirror in like a different cluster. It could be in the same cluster. Usually that's not a direct use case because you could just have a replicated stream, but typically it's like I have 2 clusters or 3 clusters and I can create a mirror in some, some other cluster. And this can be used for like DR purposes, disaster recovery purposes, or you could be able to have, the clients connecting to a cluster reading from that stream, from that mirror stream that is asynchronously replicated from the source, okay? So you can think of almost like with Postgres, you have active passive databases, right? The active is the writer, you have the passive async replicated over here, but you still can have read-only queries against it, and you're like optimizing for latency. So that's useful. NATS has had this for quite some time. But one thing that has been sort of not a pain point, but something that has been observed is like, what would be really nice is if in a disaster recovery perspective, I'm able to promote my mirror that already has all the state of my origins stream to be the primary. So what I just did, I created my origin stream, my primary, and then my mirror in 2 separate clusters, C1 and C2. I'm going to watch, just for funsies, watch my stream report here. Shrink that a little bit so you can see stream report, events, in events 2, very exciting, replication report, it's a mirror. And then I'm going to start this slow publisher as like a benchmark command. And all this is doing is just like, and you can start seeing on the top 6 messages. So it's going to the event stream, it's being mirrored to the events 2 stream, okay? So now what we can do, and we have plans to make this a little bit more elegant, but just trust me on this one. What we can do is basically now demote the first stream. Right now, we have to basically either, again, this is more of a DR scenario, so the stream could be gone, it could be deleted, it could be, whatever. Right now, I'm just going to mock this and say, I'm just changing the subject of what this stream is listening on, and I'm going to edit the events 2 stream to be no mirror, so disable mirroring, and basically promote this to be listening on these subjects. So I'm going to do this, and you'll see the top now change. So I just promoted without this guy skipping a beat. So I just moved this, I basically promoted a mirror to the quote unquote leader of the origin stream, and they were living in 2 separate clusters. So that's kind of cool. I think I'm out of time, but I kind of want to keep going. This is the last one. All right, promise. So message tracing. So this is just a fun utility. And I'm going to do a little bit of setup, and I'll explain sort of what this looks like. But the idea behind this is that you can drop a message in a NATS system, you can publish a message, it can flow through the system, and you can see where did it go. So what I'm going to do is create a stream. I'm going to create a subscriber down here, another subscriber, and these are all like sitting off of different leaf nodes or clusters and things like this. And then we'll see sort of the output here. So now I drop a trace message. And so before I go into all this nonsense up here, we can see that this message has traversed the system. It traversed 3 different route connections, which means the connections between individual servers within a single cluster. It traversed 2 leaf node connections. It traversed 2 gateway connections. It traversed 2 client connections, and then it hit a stream. So that single message flowed across that, and we were able to trace end to end how it, this is a little bit inscrutable. But if we go back to this guy, if we just, as one quick example, we have leaf node C3, C3L3 went to C3N1. So if I won't do this whole thing. L3 went to N3. So that's what the server it was connected to, and it flowed through because that's where it was published from. And then we did a router from N3 to N1, so it traversed here. And then it stopped that particular message, stopped here because that's where the stream was stored. So we had a little stream hosted here. So it said, I'm ready for delivery, but the cool thing with message tracing is it actually doesn't deliver the message. It doesn't poison your system. You just let it flow, and then it stops, it terminates right before it actually gets delivered to the final destination. So you can see it flow. You can opt into it if you want to, but generally, it's really just to see how is it flowing through my system. It's really great when in production, things are going, but you're not getting deliveries. And like, why is my subscription, why is my stream not getting the messages I expect it to get? You drop a message in, and you see it flow, and you'll see where it doesn't actually go. And you can debug the connections that are offline, there's errors happening, those types of things. So like that's one path. And then like the second one goes through a gateway, you can see through a router, through a leaf node, and then the client connected to that leaf node, and then so on and so forth. So it's a really nice thing that you can basically, because it is an end-to-end system, you can see how a single message can just flow, in all of its destinations. Oops, sorry. And I am going to wrap up there because I am well over time. I appreciate, let me just turn off my pen. So the gist of it here is that, there's a lot have been happening over this past year in these past 2 releases. A lot that was not covered. If you're curious about any of these particular ones, a lot of the team is here. So please come by. We have a bunch of resources. We're at this booth 545. This should actually say Cube Hunt, and my coworker's gonna yell at me. But we have a super cool game that you can win some fun stuff. You can just pick up a t-shirt too if you want that. We have a new color t-shirt this year, which is exciting. But yeah, thank you for your time, and I think we're at a time on the recorded side, but we'll be here after the talk, and you can always swing by the booth as well.